Assalamu alaikum. Now let's take an important example and an application for the gradient, and it is highly used in science and engineering, especially in machine learning, which is the linear least squares. Okay, so let's say that we have a vector valid function as we had before. So this f is a vector and takes another vector. In our case here, the input we call it theta, and the output is y hat, okay, which is a linear function. Phi is a matrix. Okay, now this is a simple form. It's a linear function, but it has an engineering interpretation in many cases. So let's say that we have a set of observations y of some phenomenon or some rule, right? Usually y is very complicated with respect to theta. So theta is our variables. We want to relate y to theta. Now usually in engineering we have two cases. Either that we don't know the actual relationship between y and theta. So let's say let's take this thing out here. And let's say okay, we have y, which is a vector. There's some kind of governing relationship between y and theta. So this is a vector valid function, right? Now we have two cases. Either that this function is very complicated, or we don't really know it. So what is the option here? What can we do? Usually what they do in engineering, they replace this complicated function, or f, let's say f, right? This complicated function, they replace it by a simple function. Usually what is the simplest function that we know? It's a linear function. If we don't know it, or it's very complicated, so we replace this f by phi, which is a matrix, multiplied by theta, which is the features, as we say in it's the unknown parameters, right? As we say in estimation jargon and in machine learning jargon as well. Okay, phi is called the feature matrix, which is the assumed relationship between the parameters and the outputs or the observation that we get, right? Okay, so the feature matrix is usually known. We devise it, we assume it. What is unknown is theta. So the whole thing is we want to find theta such that the approximated values of the observations are close in some sense to the actual values y, observation values, I mean. Okay, what they do usually in engineering for a very long time is to use the least square sense, meaning that okay, I want to find theta such that y hat, which is our estimate, our guess, is close to the actual observations y in the least squares sense, meaning the square errors is the least that we can get, right? Or in other words, we want to minimize the squared error. What is the error? It's the difference between y that we observe, the data that we get, and y hat, it is the estimated data. How we get the estimated data? Simply by multiplying phi, which is a known matrix, by an unknown vector. So the whole problem is that we want to find this unknown vector, theta, okay, such that the square error is minimized. Okay, so now we're talking about minimization problem, or as we shall see later on inshallah, it is an optimization problem. Okay, again we want to find theta, the vector of unknowns parameters, such that the error between the actual data that we get and the assumed model that we assume, which is y hat in equation 3.25, is minimized. How would you do that? We know from basic calculus that we can find the extreme values, which might be minimum values or maximum values, by taking the derivative of the function and set it to 0. Again, let's go back in our memories to the elementary calculus courses. So let's say that let's go back up right here, since we have, oh, I think we have here, right? Okay, here. Let's take another page here and go back in memory to the calculus courses. Let's say that you have a function f of x, a one-dimensional function. Let's say it is something like this, right? This is x, this is f of x. Now we have extreme values, mean maximum and minimum values. So this is an extreme value, right? This is an extreme value, this is an extreme value. So this is a maximum, this is a minimum, this is a maximum, this is a minimum. Okay, how do we find those values? Simply we take the derivative of x, of course with respect to x, and equate it to 0 and solve for x. Those values of x, let's say this, so this is x0, this is x, should be x, this is x2, and so on, right? We have the same case in our linear least squares problem, right? So this is our function. We call it the cost function or the loss function in machine learning. In estimation, we call it the cost function, right? Objective function in optimization. It has many names. Anyways, so this is our function that we wish to find its minimum value, its extreme value. How we do that? We take the derivative and we set it to 0, right? And we can do it in a nice way. So we want to take the derivative of L with respect to theta, right? Theta is the parameter that we want to find. Now here, L, the loss function, is a function of the error, and the error is a function of theta. So we have, actually, you can say it like this, okay? I have L, which maps to E, it's a function of E, and E, it's a function of theta, right? So if I want to find the derivative of L with respect to theta, I need to use the chain rule, which is simply here partial L by partial E times partial E over partial theta. Okay. Now again here you need to be careful, right? This is a gradient. A gradient is a raw vector, right? So you need to be careful. Anyways, let's look at the function of the error. The error is simply the norm squared. The norm squared is E transpose E, right? So if we take the derivative of E transpose E, we'll get 2E transpose. How did you get there? How did you get there, right? Okay, so I think we should elaborate a bit more. Okay, so sorry, let's turn off the marker and go down here, and let's, okay, zoom in a little bit and say, okay, my loss function is E transpose E, right? I want to take the derivative. It's not very obvious how to take the derivative of this form. When you are in confusion in the vector format, I suggest that you go to the scalar format. This is equals what, right? This equals the summation of the elements of E. Let's, okay, what are the dimensions of E? Let's say E is D dimension, sorry, E is what? E is E here depends on y. Y is it's n dimension, right? Here y, this is y. So the counter should go from 1 till capital N, right? And this is e sub I squared, right? Okay, now I want to take the derivative with respect to e sub I, right? Partial L over partial e sub I, right? This equals what? 2e sub I. Now gather those components or derivatives. So I want to partial L over partial E vector. This equals what? 2e1, then 2e2 until we get 2en, right? If you take the 2 as a common factor, you are left with this, right? To e1, e2 until you get en. This is nothing but the transpose of the vector e, because the vector e is a column vector, right? Okay, so returning back here. So this is how we get this. Now, what's the value of e? We call that e equals what? The error y vector minus phi matrix times theta vector. When you take the transpose, so you get y transpose, and then this. Okay, so let's take the transpose, this and this, right? This equals y transpose, of course, minus phi theta transpose. When you take the transpose of matrix multiplication, you flip them, right? So this equals y transpose, then you flip those two, theta transpose multiplied by phi transpose, which is equation 3.29, right? So this is the first part of the chain rule, right? So this is this part here. Now the second part here, you want to take the derivative of this. Again, let us write it down here. So we need to take the derivative with respect to theta of what? Y minus theta, sorry, phi times theta. Okay, y is a constant, so it goes away, right? We're taking the derivative with respect to theta, and this is a constant, so we're left with the constant, and of course we don't forget the minus sign. It's very easy. Okay, now we put the both of them here, right? This is with this is the partial derivative, so this is, as I said, L with respect to E, and this is what's E with respect to phi. Okay, we multiply them and we get equation 3.31 or 31. Now we need to find theta. Theta is unknown. We set this to 0, right? And now we use some basic matrix algebra, right? So we expand this term, we get those two, then we move this thing here, or that term here, right? Now what we do here is that we just do a small trick. We take the transpose of both sides, right? And we arrive here. So this, we go from here to here, actually take the transpose, right? Then this is a matrix, and this is a vector. You multiply by the inverse, of course, and you get this. Of course, theta should be full rank. Otherwise, theta transpose theta will be rank deficient, and it will not have an inverse. So this is the final result. Okay, this is the least squares error solution for our problem, and this form is very famous, very popular in science and engineering, the linear least squares estimation or estimator of a model, right? So the trick here is how to choose the matrix phi, the feature matrix. Okay, and you see that this comes up in regression, in estimation, in machine learning, in many disciplines. Inshallah, we'll see it again in the coming chapters as well. Assalamu alaikum.